Hello, my friend, and welcome in this new devlog recording for the NervLand project. Sorry. So it's been a long time since I made the previous recording because I was on vacation. So it took me some time to get back to my projects. And on top of that, what I'm going to be discussing today is a new component that I'm trying to implement in the NervLand engine, and it's a pretty complex system. So it's still work in progress, and it's taking me a lot of energy to figure out what to do. Basically, this is all about the ProLand project. Let's just switch to my screen display, maybe. Okay, so ProLand, in case you don't know what it is, it's another kind of a 3D engine created by Inria in France. So it was, I think, mostly focusing on trying to display the Earth realistically and maybe other planets also. And I'm not sure it's really active anymore. I mean, yeah, you can. I have some links here, so you can have access to the main page for ProLand, and also there's a GitLab repository. Actually, I have worked this repository, even if actually I've been monitoring this project for a long time, and I have copies of the sources that were taken some time ago, actually. Anyway, yeah, not sure there's much going on concerning this project lately. So you see, it's not really moving. And the point is, it's a product which is using OpenGL as the backend. And this I don't want to do myself. I want to use a WebGPU backend. So while working on the implementation for that, I'm actually refactoring the code and I'm getting rid of the OpenGL backend, which was another library used in there, which is called Orc, OpenGL rendering kernel. And yeah, that's why it's a bit tricky to do it because ProLand and Orc are really integrated. I mean, Orc is really integrated into ProLand, and so I'm trying to remove that, which is a bit like chirurgical operation, I guess. But anyway, yeah, I'm making some progress, and we'll see where we are with that in a moment. What I could say maybe is, yeah, if you go on this home page, you can have a look at the gallery to see what kind of display this engine could produce. So there's a lot of display for terrains. And yeah, I guess I'm not going to show everything like that, but you could have a look. There are also some very interesting algorithm implemented to render the ocean, same for the sky. You can process the terrain data dynamically and you can modify elevation data, for instance. And lately, they have also been working on some advanced algorithm to display a lot of trees, really a lot of trees. In fact, if you go on the videos, you will get access to different recordings on YouTube. I think this one is the latest one. It's going from the latest one to the first one. Where is the display? Okay, so here, for instance, is what you could observe displaying trees. And from my perspective, this is really good. And again, this was done with a pretty old hardware. Nowadays, I would expect this to run even more easily on the GPUs that we have. Anyway, very interesting to look at. You and yeah, the ocean also maybe a quick look. It's very nice. And yeah, let's just focus on what we have been doing lately. So, first thing I should discuss is the new mechanism that I have to build a scene, actually. Because if you remember a bit the latest devlogs, where do I have that? In the test, WebGPU, what is the latest one? Before the scene, let me see what it was. Okay, so the latest real example that I made for WebGPU was this one, the PBR texture, which is the full PBR pipeline with material textures. So what we're doing here in the setup app is we are basically taking care of creating a camera, creating a render pass, then adding a render node to this pass. And then we need to get access to the render pass itself and request a rendering of this pass for every frame. So we had a render frame function here where you would do that. There's a pre-rendering step, then you get some render passes. Actually, there's only one here. You render this one and you submit that, which is the first way to do it. But I feel that in the end, it would be more appropriate to have some kind of scene management system. So this is what I have introduced in the next step. So there's another example for that. So simple scene here. In this one, setup app, what you're going to do is you use a scene manager instance, and there's only one of those, of course, and you would just be able to request the creation of a scene with a given name, and by default here you would use a default scene anyway. And then you use this scene as higher level of abstraction to construct whatever you want to display in the scene. The first thing you could do, for instance, once you have a scene, is to declare that you want to add a rendering pass, a render pass. But then your render pass is going to be managed by the scene itself, so it's encapsulated into the scene. And then you can still use the scene itself and, for instance, do that. Request the rendering of a skybox. And the idea is I'm going to extend the scene to support different stuff. And you could imagine that at some point, the scene could have to manipulate multiple render passes, and you could want to render something with a technique which could be a bit complex and would require, for instance, that you render the same object multiple times on different render passes, and then you combine those together to produce additional visual results. So yeah, the idea is to have a simple interface then in the scene, which is a high-level interface, which is going to encapsulate all the details like that. If you want to combine multiple render passes mostly. And yeah, technically, for instance, for this one, the throw skybox is just going to use whatever is the current render pass, so the one you just added before, and it's going to render a skybox given the details that are provided as arguments here. Joe PBR is another of those well, upper functions, and it's doing exactly the same thing as what we were doing before in the PBR texture example. So it's going to construct this kind of node here with some inputs provided as construction threads, and it's going to add that to your current render pass. So yeah, you provide those infos here. You can provide the IBL, the transformation you want, then a list of texture names. I mean, no, this is texture names and this is a model name. And that's about it concerning the scene system. It's well, just a draft version for now. I'm going to extend that further, and I hope it's going to make more things progressively, and if it's not, then I'm going to move to something else. We'll see. Anyway, is there anything else to mention concerning this part? Not really. Next thing I would like to discuss is yeah, this concept of Frustum planes extraction from a matrix, because this was a bit new to me, so I had to spend some time working on that and thinking about it. So let's just open maybe the reference pages, this one and this one. And so why did I do that first? If I remember correctly, it's because when I started to implement one of the base classes for ProLand, this Frustum extraction from a matrix algorithm was used. So let me find this back. Okay, I just found it. It's in the terrain node class, which is one of those core classes that we find in ProLand. And the terrain node, basically, it's you can imagine that it's going to be the object in your scene that is controlling a complete terrain. So this terrain can be then divided into quadtrees, and it's going to be updated dynamically for every frame, but the terrain node itself is a parent object, if you want. So when you process such a terrain node, you need to extract the Frustum plane from your matrix. Actually, there would be different ways to do that, because if you have access to your camera, and if you store the projection that you're using for the camera, you can probably more easily extract the Frustum planes. Or more easily, maybe not, because in the end it's pretty easy to do it this way, so probably you want to do it this way anyway. But still, do you understand that? It's a bit tricky, because the idea is really you take a matrix, which is a combination of all the matrices that you need to transform a model. So the model U projection matrix. What this model U projection matrix is doing is it's going to take your object coordinates in a source frame, and it's going to convert that into the projection, actually the clip coordinates, or even further than that, the normalized device coordinate, NDC, right? The difference between clip coordinates and normalized device coordinates is basically that for the clip coordinates, you have some kind of rectangular shape. I mean, it's a box, a rectangular box, and the dimension of the box on the horizontal and vertical axis, for instance, can go from minus W value to plus W value, and the same thing for the vertical axis. And for the Z axis, it depends on the convention that you have, because for OpenGL, for instance, it's going to minus W to plus W, or the opposite, never quite remember. And for DirectX, it's going from 0 to W. And then when you have your vertices in the space, the clip coordinates, you're going to divide everything by W to get to normalize device coordinates. So from -1 to 1 then. And I think, in fact, we have, maybe not on this page, no, it's, and I get the other one. Here you have the inequalities that I mentioned. So for the clip coordinates, you're going to do take a vertex, some x, y, z, and w will be 1. so XYZ coordinates, send that into your transformation matrix, and you will get X prime, Y prime, Z prime, and W prime in this case here. W prime might not be 1, but then so you would get those coordinates in clip coordinates, and then you would divide everything by this W prime, and you would get to the normalized device coordinates this way. So the key here is really to use those three, these are actually 6 inequalities. And those 6 inequalities here, these are what will in fact define what is your frustum. Because the idea is, when you're in your clip space, if you just consider the x-axis, for instance, what is a pixel that is going to be shown? For the pixel to be shown, it must be between minus W prime and plus W prime. Those minus and plus W prime values are defining the box, the clip coordinate box, containing all the vertices that are visible. Everything outside of this box are not visible. And in fact, your matrix is going to handle the transformation from your local frame, considering a perspective transformation, for instance. So you could have view frustum that are defining a perspective. So a view angle of, say, I don't know, 60 degrees and an aspect ratio of 1.3, whatever. And this view frustum is going to be transformed by the matrix into this box. And so then you can just use the inequalities on this box, and this, the right side of the box, for instance, is going to be matching your projection right plane, and the left side of the box is matching the projection left plane. So yeah, the equation that you have here for the prime coordinates are defining exactly those frustum planes that you want to retrieve in your source coordinate system. So you start with that, and from there, actually the computations are pretty easy to do, and I have tried to replicate that here with some, I would say, custom details that allow me to understand better what I'm doing myself, but maybe it's not so clear for anyone else. And let's see anyway. As I said, you have a transformation matrix. It could really be anything in the hand, as long as you have the projection integrated into this matrix. You could start from anywhere, either from the local frame of the object, or the world frame, or the camera frame, whatever, and it's just going to define what is going to be the frame where you get your frustum planes defined. So if you start from the world coordinate, for instance, the matrix here will transform world points into your clip space, and the computation that you will do will allow you to find the coordinate of the frustums in the world coordinates. So what you need to do exactly is you just consider what kind of transformation you're doing on your vertices. So if you're given a vertex, let's call it V here, so you have those coordinates X, Y, Z, W, and you will transform that using the matrix to produce the image of your input coordinate. So X prime, Y prime, Z prime, and W prime. Then you need to use each of those inequalities one by one. And if you start from the first one, for instance, that's going to define your frustum left plane. And you just start with that. Minus W prime should be less than X prime. And then you just replace the value that you have for X prime and minus W prime by the corresponding element here. And for instance, to compute x prime, what do? You take your vector and you multiply, you use a dot product with the first row of your matrix here. So I guess you can imagine that. Take the vector, you take the first row, and that will give you x prime. And for the w prime, it is the same thing. You take the vector, but you take the last row, so row number 4, and you compute dot product to produce w prime. So I have just replaced w prime here by its value, and x prime here by its value also. And this inequality is the same thing as 0 should be left at this inequality, this value. And then, in fact, in V, you have those x, y, z coordinates in your source frame. Remember that. And what you can also take for granted then is that in your source coordinate, the w value, this one, is going to be 1. So this inequality here, you can turn that into, well, 0 should be less, or you can take 0 equal to get the plane coordinates itself, because when you say 0 should be less than the value, you're considering all the points that are inside your view frustum. But if you just want the plane, that's where you have 0 equal. And yeah, just replacing the value that you have for row 1 and row 4 here, you get those matrix elements here. And this is exactly the equation that you have for the left plane of the frustum. And this is really cool if you ask me, because in the end it's very simple to compute. There's no real tricky complex mathematics involved on the matrix itself. And yeah, that's it. So you just need to do that. Then for the other inequations, this one and the 2 here and the 2 here, it also depends. That's what is explained here. It also depends on the convention that is used depending on the graphics API that you have in the backend. Because for instance, as I said, for DirectX, the value for the z-axis is going to be 0. So the clip box is starting from 0 and going to w on the y, on the z-axis. But for OpenGL, it's not quite the same thing. You have it. For OpenGL, you have this minus w also on the z-axis. And then, yeah, depends also on the convention of your matrix multiplication order, because what I have here, for instance, I'm assuming that I'm performing post multiplication, so matrix times vertex to do the transformation, which is, I believe, the convention you're supposed to use for DirectX. I guess we could see that here. Yes, because it's mentioning the rows. It's not explicitly written anywhere, right? Yeah, no, it's here, MV. And no, that's for OpenGL. Okay, for OpenGL, you use matrix post multiplication, but for DirectX, yeah, you use matrix pre-multiplication. And I guess in my case here, I'm still relying on post multiplication anyway. So this is what I've used as a convention. But yeah, you need to take care of that, because it's going to change the equations that you want to solve here, whether you use post or pre-multiplication. So to keep in mind. And in the end, yes, this is going to produce a function like that, where you start with whatever matrix that you want, and you can extract the frustum coordinates, the frustum equation directly. In this equation, by the way, in case you're not familiar with that. We have the x, y, z values here, and those elements, this one here, here, and here, are defining the normal of the plane. And this last element here is used to ensure that you're going to find a point on the plane here. So yeah, that's it basically. Okay. After working on that, I could actually get some initial display on the quadtree system that we have in the ProLand terrain, because as I said, there's a terrain node, and in the terrain node you actually have a root quadtree and a terrain quad, and this quadtree can be subdivided depending on the distance that you have to the camera, actually dynamically. So I think I made another example for that, and what I've maybe not shown already is the second example that I have here. I guess I could show this quickly. Let's begin the ring simple 2. Not quite. Let me find that. Actually, no, it's just simple 1, because the other one is simple terrain. And here we go. So what you have here is another very simple example where we have a terrain node, and we have those terrain quads that are going to be subdivided progressively depending on the position of the camera. And you have here the count of total quads that are displayed. The only real difference that we have compared to the other example is that here we have a shader at play that is going to actually use the coordinates that you have for those different quads to build this sinus wave that we see in white and black. And to build that independently of the quad resolution. And so you see that we're not breaking the pattern itself depending on what we use as a resolution to render those quads. And yeah, that's it. So not much more going on this one. In fact, yeah, that's why I actually didn't produce much more visuals so far, because after this point we're going directly into pretty tricky territory. Because let me just show you that for the basic example, that's what I use as a template actually. This is going to not use much from the ProLand framework itself, just your terrain node and a specific shader to render the quads. But yeah, in the end, it's still pretty simple. Where do I have detail about? Yeah, that's the shader basically. So you're just doing this kind of transformation, and that's it. But now, yeah, moving to the next step, I need to implement the basic terrain example. So this is going outside of the core component of ProLand itself. So yeah, can I show you that? If I go into documentation, if I go onto terrain API and the examples, let's just start from the API and the examples. So for the API itself, now we're going to try to use the producer system that we have in ProLand, and this is in fact the tricky part to implement. The producer is some kind of a framework, if you want, that is going to produce different level of types. So yeah, we're rendering those tiles in the quadtree, but it's going to produce texture data and other kind of data for each tile at each needed level of details. And it's going to use the task graph framework itself, which again is another part of the orc library. And this task graph is used to allow computing different tasks in parallel using multiple threads and multiple cores on your system. So that's cool. But as I said, I don't want to really integrate the orc library, so I'm removing this part. But I still want to use the task graph, so I'm trying to re-implement this part. But at the same time, also the task graph in orc was implemented in such a way that you would only really perform GPU related tasks from a single thread, and you can use multiple threads to perform the task only for what are considered to be CPU tasks. And that makes sense when you're using OpenGL because you don't have any kind of free thread safety or anything. But for WebGPU, it's not true anymore. I think we can, I mean, I've really not checked that, but I definitely assume that's true. With WebGPU, you can post command buffers. It's called the command buffers here. I don't remember. Command recordings, command. I don't remember what it is. Anyway, you can post your request to the GPU to perform some stuff from multiple threads, and it should work. So when building my own task graph, I need to ensure that I'm not constraining those tasks to execute on a single thread when we have to do some kind of GPU operation. Which means, yeah, quite a lot of stuff going on together, and I need to fix and change and actually really understand what's happening in those classes while I am updating them. So that's why it's a bit slow. And the idea then is to try to, yeah, kind of get this first terrain display. It was similar to the previous terrain, but you have elevation information here. And I think it's actually using elevation information and normal data. So once I get those two ready, well, that would be super cool. But I'm not to this point yet. So yeah, this is still pending. Anyway, after that, as I said, I started to work on the task graph and the multi-thread scheduler. Oh, and it's already pretty long. So actually, that's a good point where I could stop the recording, because then we're going to focus on the log manager and some interesting improvement that I made on this class. And log manager is a generic class which is not really related to ProLand itself anyway. So yeah, that's good. Okay, so let's stop this recording and we continue another session then on what is left from this devlog. Thanks for watching and see you another time. Bye bye.